Moving a metal bar on two parallel rails. You're conducting an experiment in which a metal bar of length L, 6 centimeters, and mass m, 0.2 kilograms, slides without friction on two parallel metal rails. So it's sliding on these rails. A resistor with resistance 0.8 ohms is connected across one end of the rails so that the bar, rails, and resistor form a complete conducting path. So this is a complete conducting path. The resistances of the rails and of the bar are much less than capital R and can be ignored. The entire apparatus is in a uniform magnetic field B that is directed into the plane of the figure, into the page. You give the bar an initial velocity v is equal to 20 centimeters per second to the right and then release it. So we have an initial velocity and then it is released. So that the only force on the bar then is the force exerted by the magnetic field. So it's the magnetic force. Using high-speed photography, you measure the magnitude of the acceleration of the bar as a function of its speed. Your results are given in this table. Part A, plot the data as a graph of A versus V. Explain why the data points plotted this way lie close to a straight line and determine the slope of the best fit straight line for the data. Okay, so we have this bar moving on these two parallel rails, frictionless rails. Now you can see that as this bar moves to the right, the flux in this conducting loop is increasing. So there must be an induced current that opposes this increasing flux. That means it has to be creating a magnetic field inside the loop out of the page. Using the right hand rule, the thumb points in the j-hat direction, the four fingers basically point out of the page when the current flows counterclockwise. So you can see that with this, we're going to get Lenz's law satisfied. It will be opposing the increasing flux into the page. Now this will create a magnetic force on this bar, IL cross B. So L vector is in the direction of the current. So four fingers of the right hand point in the direction of the current and curl towards the magnetic field into the page. The thumb of the right hand points to the left in minus I hat direction. So you can see this force is trying to slow down this bar. Okay, so this is our understanding. Now the area of this conducting loop is its length L multiplied by the width W. So length multiplied by W is the area. The magnetic flux phi B is the magnetic field multiplied by the area. So it's BLW, but I note that W is a function of time. And the speed of this bar, V, is basically dW dt. Okay. So if I look at the rate of change of this flux in time, d phi b dt, this is equal to B times L d omega dt, which is B L V, the speed of the bar, and the induced EMF, so there will be an induced EMF on this bar, which has a magnitude d phi b dt. So this is equal to BVL. So we can calculate the current that is induced on this bar. Since we're neglecting the resistance of this bar and the rails, the only resistance that is significant is this capital R. So the current induced will be epsilon divided by R, which is BVL divided by r. Now, what is the magnetic force that this bar will feel? A conducting wire feels a force in a magnetic field, IL cross B. Now you can see that due to my argument, the magnetic flux into the page is increasing in this loop. The current must create a magnetic field out of the page inside this loop. So using the four fingers of the right hand following this current, we see that our thumb points out of the page when the current flows counterclockwise, which means the L vector is in j hat direction, in the direction of the current. So I, L, j hat cross with magnetic field in minus k hat direction. So I have defined k hat in the direction out of the page. So z-axis is coming out. So with that, I see that this magnetic force Fb is the current, which is BVL divided by R, L, B, J hat cross minus K hat is minus I hat. So that you can see here with the right hand, the four fingers of the right hand point in J hat direction, curl towards minus K hat, the thumb points in minus I hat direction. So that's the force opposing the motion of this bar. Okay, so looking at this force Fb, we see that this is minus, so I have two b's here, b square, l square, v over r. So I will obtain minus b square L square V divided by R in I hat direction. That's the only force acting on this bar. So this is mass times acceleration. This is ma in minus I hat direction. So you can see from this relationship, if I look at the change in acceleration and change in velocity, the ratio of change in acceleration to change in velocity is b square L square over mr. Okay, so the slope of acceleration versus speed curve, delta A over delta V, is equal to b square L square divided by mr. This is a linear relationship. Okay, so I have shown that the slope is a constant. Actually, if I plot this data, given in the table, you can see that I indeed obtain a linear relationship between acceleration and the speed. Okay, so that's the slope. So in part A, we have explained why the data should lie close to a straight line, and we have determined the slope of the best fit straight line for the data. So that slope is basically going to be used in part B. Use your graph from part A to calculate the magnitude of the magnetic field. Now the slope of the best fit to this data is delta A over delta V. So that's roughly, taking these two data points here, 6.2 at 20 centimeters per second, and then we have 2.5 at 8 centimeters per second. So these two data points give me 6.2 minus 2.5 divided by 20 minus 8, 0.2 0.308 second inverse, and that's equal to, from my analysis in part A, B square L square over M mass times resistance. So this tells me that the magnitude of the magnetic field is 1 over L square root of the slope multiplied with mr. So that's how I should calculate the magnetic field. Plugging in the numbers, B is equal to 1 over the length, 1 over 6 centimeters, 0.06 meters, square root of the slope of the best fit, 0.308, a mass 0.2 kilograms, resistance is 0.8 ohms. So this gives me a magnetic field magnitude of 3.7 Tesla. So that's the answer to part B of the problem. Moving on to part C, while the bar is moving, which end of the resistor, A or B, is at higher potential? Okay, so let me make it clear that this current has to flow down from A to B, so A has to be at a higher potential. And the argument is as follows. We have the magnetic force FB pointing in a direction that opposes the motion to point in minus I hat direction. The L vector should be in J hat direction. That means the current I flows counterclockwise, so that the potential of A is greater than the potential of B. This creates a magnetic field out of the page in K hat direction to oppose the increasing flux into the page direction, which is minus K hat. So basically, this satisfies Lenz's law. All right, so we have determined A has to be at a higher potential compared to B. So the current flows counterclockwise. Okay, now let's move on to part D. How many seconds does it take the speed of the bar to decrease from 20 centimeters per second to 10 centimeters per second? So we have the equation of motion, minus B square L square V divided by mr, the slope, is the acceleration. The slope multiplied by v is the acceleration, which is dv dt. Okay, so if I isolate time on the left hand side, so I'm going to have dt is equal to minus mr over b square L square dV over V. So this went upstairs. mr over b square L square dV over V is dt with the minus sign here. Now, if I integrate both sides from time t is equal to 0 to time t, so this is going to be a dummy variable now, integrated from the initial speed v0 to the speed at time t, v of t, I'm going to obtain the integral of dt is t, evaluated between 0 and t is t, minus mr over b square L square natural logarithm v divided by v0. So that's how I should calculate the time it takes to reduce the speed. So you can see that this t is equal to minus 1 over the slope of delta A delta V, natural logarithm V over V0, and we're looking for a speed of 10 centimeters per second, so minus 1 over 0.308 natural logarithm. Starting from 20, we go up to 10, so 1 over 2, 10 over 20, natural logarithm of 1 over 2. So we find the time it takes to be 2.25 seconds. That answers part D. Okay, so in this problem, we've looked at a bar that is conducting bar moving on two rails. Because as the bar has an initial velocity v moving to the right, the flux inside this loop is increasing. There has to be an induced current that opposes the increasing flux, so generating a magnetic field out of the page. Current must flow counterclockwise. Current always flows from high potential to low potential, therefore A is at a higher potential compared to B. That was the answer to part C. The magnetic force Fb is IL cross B. L vector is in the direction of the current, so you can see that this will be in minus I hat direction. The induced EMF is given by Faraday's law. The magnitude of the EMF is d phi b dt, which is BL d omega dt, because it's magnetic field times the area, dot product of magnetic field with area vector, but the area is changing in time because omega is changing in time. The omega dt is V. Epsilon is BVL, so current is BVL over R, substituting into magnetic force. BVL over R, L cross B, LB in minus I hat direction, we find that there is a really linear relationship between acceleration and the speed. The acceleration is minus b square L square V over mr, so that delta A over delta V is b square L square over mr, which is a constant, so it's a linear relationship between acceleration and speed. Actually, when we plot it, we see this linear relationship. The best fit to this linear fit to this data gives us 0.308 inverse seconds. For b square L square over mr, that's the slope. So from this we can pull out the magnetic field, 3.7 Tesla. And in part D, looking at this equation of motion, net force is the magnetic force, minus b square L square V over mr is dv dt. So m times acceleration is the net force. And isolating the speed and the time goes to the left, the speed goes to the right. We obtain this relationship and we integrate it from time t equals 0 to t. uh, and we ask for the speed to go from its initial value to 10 centimeters per second, we see that this integral gives us this natural logarithm relationship between time and the speed. And from this, because the prefactor here is 1 over the slope of acceleration versus speed, we can obtain the time to be 2.25 seconds to reduce the speed from 20 centimeters per second to 10 centimeters per second.